This conference will now be recorded.
Good morning to everyone. Until now, I have discussed about the what is meant by Magnus effect and how aerodynamic takes place because of Magnus effect, in case of a spinning ball, etc. So here we mean the dynamic lift. We can define it as the force that acts on a body, such as the airplane wing, hydrofoil, or the spinning ball, by the motion of the fluid. So if you see airplane wing, so it just the air and ultimately fluids the hydrofoil, like a hydrofoil, airplane wing is similar. And here if you see hydrofoil, when it passes into liquid, you can consider the hydrofoil. The actual path will be different from that of the expected path amount. The actual path will be different from that of the expected path. So how we can see? So if you see, for example, here, and this deviation is due to the Magnus effect, which we call it as known because of the spinning of the ball.
Our Earth is like a treasure chest. We have to watch over and look after.
So I'm back at the University of Sydney with Rod Cross.
Hello, Derek.
And today we're talking about the effects of air on projectiles.
We are.
Now, normally we neglect these effects. When I'm teaching students about projectiles, I tell them, forget about the air, let's just talk about gravity.
Because it simplifies the problem. That air is real, it's heavy stuff, and it affects the flight of all projectiles.
All right, well, why don't we do a little experiment to show the effect that air can have?
This is a surprising experiment that we've set up here. First of all, I'll show you what happens to a tennis ball when it rolls down this inclined ramp.
Well, that falls exactly like I would expect, basically a parabolic path.
As predicted, but let's try something a little bit lighter, such as this paper cylinder.
Okay.
Weighs only a gram or so. The effect of the air will be more important. Watch what happens this time.
Okay. Whoa, so the paper cylinder goes backwards. That doesn't make any sense. I mean, it was rolling forwards off that ramp.
No, it does it every time, and it's because of an effect known as the Magnus forces acting on the spinning cylinder, acts on a spinning ball as well, and people who play sport know about it. They wouldn't call it a Magnus force.
Why is it called the Magnus force?
Because Magnus was the first guy who discovered it when he was investigating why cannonballs curve as they propagate through the air.
Uh-huh. And so what did he find out?
What he found is that when a ball or any object is spinning like this, there's a force perpendicular to the spin axis. If it's spinning clockwise or with top spin, the force is down. If it's spinning anti-clockwise, counterclockwise, the force is up.
So how do we get a Magnus force on a ball?
As the ball's moving forwards through the air, if it's spinning, the air is flowing around the ball from the front to the back. The ball is spinning in the same direction as the airflow at the top of the ball, but in the opposite direction at the bottom. Because of friction between the air and the ball surface, air is dragged around the top of the ball downwards towards the back. But at the bottom of the ball, the airflow and the ball are opposite directions. The air comes to a screeching halt fairly soon, instead of being deflected upwards. The net result is air is deflected downwards. Due to Newton's third law, the air exerts an equal opposite force on the ball, which is upwards.
So how would sports players take advantage of the Magnus force?
They make the ball curve through the air by a different amount than that due to gravity alone. So a golfer will strike a golf ball with backspin. That exerts a vertical force, a lift force on the ball that keeps it in the air for a longer time and therefore it travels further.
Mm-hmm.
A tennis player will hit the ball with topspin. That causes the ball to curve down onto the court after it passes the net. A baseball or cricket player will also do that, but in addition, they can make a ball curve about a vertical axis, in which case the ball will either curve to the left or to the right, away from the batter.
Making it much more difficult to hit the ball.
That's the object of the exercise.
I see. So are there any other air effects that we need to be aware of?
There's quite a few, actually. There's the buoyant force acting on a balloon, for example, or any object. There's a drag force acting backwards that slows the ball down. And if the ball happens to have seams, then there's a side force acting on the ball.
Uh-huh. Well, that sounds like a whole other episode. Balls with seams. Yeah.
It is.
All right. Well, stay tuned if you want to find out how air affects balls with seams.
So here you are able to see the path is deviating with respect to the when compared to the expected path when the object is in spinning. So you can see similar examples in other videos also.
We were at this event the other day, and I saw a guy kick a ball. I was distraught over the curved trajectory of the ball. How do they do that? And since you can't get good at soccer using physics, I'd better consult a friend. Kyle! Kyle, I want to be able to bend it.
Okay. Okay, so look, I bet you that I can take this ball, set it in that corner, and bend it into that goal.
So I'm skeptical about this because you can't even see the opening of the goal. All you can see is the goalpost. And from the vector that you trace from the corner to... It's magic! No, it's physics. Do it again.
So here the ball is not passing
How
in
did
a
you do
straight line.
that?
Well, it's a pretty standard
Passing in a
technique in
curved
soccer
pattern.
to use the inside of your foot to generate spin on the ball. That spin is actually going to make the ball curve
Because of
into the
spinning
goal.
of the ball.
Let's take a look at how that happens. As Kyle kicks the ball with his right foot on the right side, he imparts a spin on the ball. The ball traveling in this direction means air is flowing across it in the opposite direction. But right near the ball, there is a thin layer of air dragged around. As oncoming streams of air pass the ball, the side moving in the same direction as the spinning ball is accelerated, follows the curve of the ball, and is deflected off to the right. The side that is moving against the spinning ball meets opposing air and can't continue around the ball. It slows down and goes straight. We end up getting a net flow of air to the right, and the ball must move left.
Wait, that's Newton's third law.
Yes, thank you, Kyle. Just like a rocket, if you push a gas one direction, namely downwards out of the rocket, then the rocket has to go up.
So what you're saying is my shot is like a rocket.
Yes. Thank you, Kyle. Like the rocket, as the air moves in one direction, the ball has to go the other direction. Also, since the air is slowing down on the right side, you get a buildup of air, which creates a higher pressure on that side and pushes the ball to the left. The airflow is extremely important. You could not make this kick in a vacuum. It's not some weird thing the ball does to itself to curve. You need air flowing across the ball to push the ball. This is called the Magnus effect.
So you can use this phenomenon to do all sorts of shots in soccer. As we already saw, I can use the inside of my foot to make the ball curve left. I can also use the outside of my foot to make the ball spin the other way, and then it curves right. If I wanted to, I could even hit the bottom of the ball, give it backspin, and send it up into the air.
With a backspin, it's actually going to curve upwards.
Finally, if I want to get real tricky with it, I can put no spin on it at all, like a knuckleball. When this happens, you get turbulence, unpredictable on both sides of the ball, and the keeper doesn't know where it's going.
Should we try the knuckleball?
That one's going to be a little tougher.
That's the physics of soccer. Thank you for your help, Kyle. If you want to see some videos of some incredible soccer players bending the ball, check out these links.
Similarly, you can also see here.
Recently, some friends of mine went to the Gordon Dam in Tasmania, which is 126.5 meters
So
or
you can see it
415
later.
feet high.
I have already
Then
sent
they
the
dropped a
links to you.
basketball over the edge. You can see that the basketball gets pushed around a bit by the bridge. Can you fix that?
So here, if you see, the ball is not passing in the expected path because of
That's
this
a hard
spinning
one
of the ball.
because this ball's a little bit magic. It's got a bit of string glued to the left side of it to make the ball curve to the left.
Why is that?
And that's because the air that's flowing from the front of the ball around to the back encounters this seam, becomes turbulent, and turbulent air is known to stick to the ball longer than smooth or laminar flow. And so the air is deflected this way to the right on the ball, and therefore there's a force on the ball to the left, and so it curves. So and this is quite a light ball, so it curves a long way.
But on a cricket ball, the seam isn't on one side, the seam is down the middle.
Correct. It's spinning in such a way that the seam's inclined at an angle to the direction of motion of the ball.
I see.
In which case, air coming towards the ball will flow smoothly around the smooth side and separates from the ball. Air flowing on the rough side, the seam side, becomes turbulent as soon as it encounters that seam, gets deflected to the left, and therefore the ball gets deflected to the right.
So you basically make a rough side using that seam by angling the seam.
With a cricket ball.
With a cricket ball.
Or you can have a rough and a smooth side, because as time goes on during the game, one side gets rougher than the other. The players maintain the smooth side by polishing it, or wherever, as if they're scratching themselves.
Right.
And then you don't really need the seam to have that effect, because the effect is just a rough side and a smooth side.
So a ball will always swing towards the rough side then?
It does.
But how does someone swing a baseball then?
That relies on the Magnus effect, normally. So if the spin is about a vertical axis, it'll either curve to the left or curve to the right.
It's a curveball.
Exactly. However, there's a pitch ball known as a scuff ball that people don't like to know about because it's illegal. And if you roughen up one side of the ball surreptitiously without anybody noticing it and then toss it, it will curve a long way, just like the cricket ball.
It'll curve towards the rough side.
Correct. However, there's an effect discovered just this year, which is fairly obvious when you think about it. You can have a smooth patch on a baseball.
But, I mean, the seam seems to be symmetric everywhere, so how can you really have a smooth patch?
Well, what you do there is to make sure the axis passes through a spot which is a large distance from the seam. In other words, right about there, it's about 1 inch away from the seam, and if it rotates about that axis, then you've got a big spot that's always smooth on that side. You've got a smooth spot as opposed to a rough spot.
And so it swings away from the smooth spot?
It does, and I can show you that in slow motion.
So you've tried this out with one of your polystyrene balls?
I have, so that you can see the effect more dramatically, but it's also on film from a real baseball match. In April this year, it was filmed and noticed for the first time that it's curving the wrong way.
So who was it who explained this effect?
Me.
You were the first.
So you can see in more detail here about the same effect when the ball is spinning, how the velocity varies on either sides of the ball, spinning ball, and as a result how the pressure changes and how the dynamic lift takes place.
Grammarly does more than catch errors. As a matter of fact, for what it
Hello. In this video, I will discuss dynamic lift, and it is caused by what is called the Magnus effect. So first, we will see what is a dynamic lift. Let us consider that a ball which is not spinning, is thrown in some direction. Suppose it is thrown towards right, and when it is thrown, the air makes uniformly distributed streamlines on both sides, above as well as below the ball, because it is not spinning. So the distribution of the streamlines caused by the air will be like this, and I have same value of velocity at the top of the ball as well as below it, and therefore there will be no pressure difference here. So if we consider 2 points, A and B, the velocity at A will be equal to that at B, and therefore the pressure at A will be the same as pressure at B, and therefore there will be no pressure difference below and above the ball, and hence it will keep on moving in the same direction in which it is thrown. Now consider the case if the ball starts. Consider the case when the ball is thrown, when it is spinning. So in addition to being thrown towards right, it is also spinning, suppose in clockwise direction. And because of this, when the ball is spinning, the velocity, the ball will apply the drag on the streamlines in the same direction, and therefore the velocity below the ball will increase. So VA and at velocity, because the streamline and the spinning are in the same direction at point A. So velocity will increase at point A and it will decrease at point B. Because at point B, the streamlines and the velocity of rotation of the ball are in opposite direction, and hence we can write that the velocity at A will become greater than that at B. And as we know that if at a point the velocity increases, the pressure decreases. Clearly, the pressure at A will now become less than the pressure at B. And because of that pressure difference, which is smaller at A and larger at B, the ball will not keep moving in the same direction. It will get deviated in downward direction. Because of that pressure difference, the force will act on the ball, and therefore, in addition to instead of moving in a straight line, it will deviate in this direction. And this effect is called Magnus effect. And Magnus effect is observed in many sports events. For example, this is observed in cricket, this is observed in tennis, and more importantly, this is observed in football, because the football is of larger size. So Magnus effect is more observed in that case. And because of Magnus effect, the ball can be made to deviate in any certain direction, because if it is spun in certain direction, it will get deviated in a direction towards the direction in which the pressure decreases because of the higher speed. So Magnus effect is observed in daily life. And in addition, if the ball is spinning in vertical direction, therefore the force will be either act in downward direction or in upward direction, depending on the direction of rotation. And if the ball is revolving in horizontal direction, the ball will deviate laterally. That is, it may deviate towards left or right. So this is called the Magnus effect. And that dynamic lift also acts in some other cases. For example, if we consider a plane moving to take off, we know that suppose the plane is moving in this direction, and if we look at its wing, that is, now I'm going to draw the cross-sectional view of the wing of a plane. The cross-sectional view of the wing of a plane is like this. Plane is moving in this direction, and this is the cross-sectional view of the wing of a plane. Plane is moving in this direction, and because the...
So this is only the cross-sectional view of the aeroplane wing, not the complete wing. It is only the cross-section of the aeroplane wing. So it will be in a plane manner. So it will be looking like a plane or a three-dimensional manner, having very long. And we are taking the cross-section of the wing. So cross-section of the wing means we are taking 2 dimensions. 3 dimensions we are limiting to 2 dimensions when we are taking the cross-section of the wing.
This lower surface is almost flat. The wind will keep moving in this direction, but at the top, the wind will have to cover a larger distance because of the shape of the wing, and therefore the speed at the top of the wing, let it be
Aerofoil.
At the top of the wing will become higher, and therefore your velocity at B will become higher than that A, and therefore pressure at A will become greater than the pressure at B, and because of that pressure difference in net force, the thrust will so there will be force in this direction on the wing, and this upward force the takeoff a plane. So this is another example of dynamic lift, and this is all about this topic. Thank you.
So you can see the same in more detailed manner here also. Here you can see how the path gets deviated from the expected path because of the spinning of the objects.
We will see the certain examples using Bernoulli's theorem, which are known as dynamic lift. When a bowler is throwing a ball towards batsman, here he is neglecting the projectile motion. We can say he is throwing ball at this direction. Okay. This is the straight line. The ball will go like this. This ball is not spinning and it goes like this. Now in the second case, he makes a spin. Okay, when he makes a spin, he can spin it this way, or he can spin it this way, in whichever direction he wants. Suppose he rotates it clockwise. Then what will happen? Again, I make the same sequence here. He is rotating the ball clockwise. When he rotates the ball clockwise, I will make it a little bigger. The ball has got a seam. Seam means there is a threading all around the ball. That becomes a little rough surface. And when the ball rotates like this, the air particles in contact with this will also move. So the ball can move air around it along the seam. Okay. The polished portion cannot, but the seam can, where we have that threading. Okay. He keeps the threading up and down, and this is magnified view here. This is the seam. And when he spin it fast, then the air moves. How the air moves? When it is going up, when it is going in forward direction, how the air is cutting it? It appears the air will come in this direction. Okay. It is going here, the air is coming in this direction. Okay. Now, suppose while throwing, he moves it in anti-clockwise direction. This. If he moves it this way, then what will happen? See, the air which are air due to its original velocity is coming. It is going here with the velocity v. So we can assume that the air is also touching it and going in this direction with a velocity v. Okay. So this has velocity v. This has velocity v in this direction. Now, this is rotating anti-clockwise. When it is rotating anti-clockwise, the air particle which are in contact with it, those are also moving. Let us say with certain velocity, and that velocity is v2. So air particles here, get an additional velocity of v2. So what is the total velocity at this layer? That is v1 plus v2. v1 was the original one, and v2 is additional created by this seam in this direction. What's happening here? Here the ball is rotating this way, and the air particles here move in this direction with the velocity v2. And now, what is the total velocity in this direction? In this direction, the velocity becomes v1 minus v2. See the ball. On the top, velocity in this direction is in this direction. It is v1 plus v2. Bottom, velocity in this direction is v1 minus v2. So here, air velocity is less. Here, air velocity is more. This is almost at the same height. So when we apply Bernoulli's principle says that v1 upon rho plus half v1 square is equal to v2 upon rho plus half v2 square. And GH1, GH2, yes, both are almost at the same height from the floor, rejected, that is cancelled from both sides. So this is the equation we will be working on. Now in this v1 plus v1, v2 plus v2, these are equal. Here, what happens? This velocity, if this velocity become larger, what will happen to v2? v2 will become smaller. If this velocity become larger, v1 will become smaller. So here what we see, the velocity which is on the upper layer is large, and the velocity at lower surface is small. So velocity at the upper level is large, velocity at the lower is small. Where velocity is small, the pressure will be high. Where velocity is large, pressure will be less. So here, pressure will be less. P less. Here, P more. How pressure work? Pressure always press the surface at right angle. So here, this pressure press the ball in this direction. Here, pressure press the ball in this direction. Now, which pressure is more? We have just discussed this pressure is more, this pressure is less. So, in which direction will be the net pressure or the net force? This is more, this is small. So, naturally, the resultant will be in upward direction. Resultant. Pressure multiplied by area will become a force. So, that is the force applied on the ball upward. So, what will happen then? What happens then? That when he rotates it this way, we see the ball is going in this path. Here. It will strike here. The batsman is ready here to see if the ball is coming here, but the ball comes here. And that is this. He gets disturbed with this. He is expecting the ball here. How he is expecting here? He has seen the ball starting in this direction. With this direction, the moment he sees the ball, he makes sure that ball is coming like this, and he keeps his bat here. But on the way, the ball just fly up. here. It flies up. If I make it very clearly, it will be slightly going up like this. Then it strikes here. So the moment he expects the ball is coming here, the ball comes here and he gives the catch. That becomes the problem for him. So this is unexpected. And this is what? This is lift of the ball. And this lift is dynamic. Dynamic means due to motion. This is what happens when the ball is lifted up. The same thing can be done other way. If he rotates the ball clockwise, then what will happen? The batsman will see the ball is coming in this direction. He is prepared here, but the ball goes like this here and jumps. That is again unexpected. See the other thing. If he does not rotate it this way or this way, he rotates it this way, then what will happen? You see here, it is lifted up. If he is rotating this way, the ball in the air, he is moving it this way, and the ball goes like this, and in the air, it will go like this. Yes, whatever you call it, whether it is a swing or whatever it is, that will happen. And if you rotate it like this, then in the air, it will go like this. And this thing you have seen in football also. When they hit the ball goes in the sky like this. Goal post is here, but in the sky, it bends like this. This way. Why? Because they have rotated it this way. So all these are effects of dynamic lift. And here, the velocity increase on one side, the pressure become less. So from the other side, it gets a push. It gets a push and it bends in the air. So this is dynamic lift. The same thing we observe in aeroplane, and that we will see in the next lecture. Thank you.
So you can see like this. So and here
Hey guys, welcome to another episode of Scientifically Explained. So, I was watching a football match between Portugal and Spain this weekend when a player named Cristiano Ronaldo kicked the ball in one direction and it swung into the goal from the other direction. I was doubtful about the trajectory of the ball. I mean, the opening of the goal was fully covered by all the players, but he bent it into the net so perfectly. So how did he do that? Well, it's no magic. Here's the physics behind it. Basically, it's a technique in football that you use the inside of your foot to generate the spin in the ball. That spin makes the football to curve into the goal. Suppose the person is right foot, and he hit the right side of the ball. The ball starts to spin. Now, when the oncoming stream of air passes the ball, the side which is in the direction of the ball will be accelerated, following the curve of the ball, deflected off to the right direction, while the other side of the ball that is opposing the air slows down and goes straight. So we get a net flow of air has right direction, and we know if the direction of the air is right, the ball must go in the left direction, which is Newton's third law of motion. That states action and reaction are equal in magnitude but opposite in direction. So if the ball on the right side slows down due to the opposite direction of air, a buildup of air is made. That makes a higher pressure on the side, which pushes the ball into the left direction. This phenomenon is called bending the ball, or curve the ball. But in physics of fluid dynamics, this phenomenon is known as the magnus effect. In this case, it's dynamics of air. We can use this phenomenon to curve the ball in any direction. If you kick the ball with the outside of your right foot, the ball will bend onto the right direction. Similarly, if you hit the bottom of the ball to give a backward spin, the ball will go up into the air. Remember, the airflow is extremely important. This phenomenon does not work in vacuum because no air interferes with the ball. Now you know. So next time you watch two balls bending like this, tell your friends about the science behind it too. Stay curious, comment below if you have any questions, and as always, thanks for watching.
So like this, we can define the dynamic lift as the force that acts on a body, such as aeroplane wing or hydrofoil, a spinning ball, by virtue of its motion through a fluid. So while the object is moving through a fluid, so based on whether it is spinning or not, the When it is not spinning, the velocities will be same and symmetrical on either sides of the object, like a ball. And then when it is spinning, the velocities of the streamlines of the fluid will be varying on either sides of the object when compared to side the another. So due to these variations in velocity, the pressure changes will come, and due to pressure changes, the dynamic lift will come. Dynamic lift will come. So as a result, the object will be deviating from the expected path when it is rotating. So this is what we call it as the in case of rotating ball, we call it as the Magnus effect, and this is also called as the dynamic lift. And similarly, when we come to the aerofoil, so here aerofoil is nothing but you can imagine it as the area of cross section of the aeroplane wing, area of cross section of the aeroplane wing. So if you see here, so this is the aerofoil or area of cross section of the aeroplane wing, and if you see it on the top of the aerofoil or the top of the aeroplane, the path is curved path. So let us suppose the aeroplane is moving from left to right. Aeroplane is moving from left to right, and the top of the aeroplane wing is bent down from right to left. And here, while the aeroplane is moving from left to right, the streamlines of the air will be moving from right to left. So because of this curved path, the streamlines get deviated. So there will be more accumulated on the top of the aerofoil or aeroplane wing, and the velocity will be more when compared to the bottom, where the surface is almost horizontal or bent down in this direction. So here, due to the so here we need to make uplift. Aeroplane have to take off means we have to apply some upward thrust. Upward thrust we have to apply, which means the upside pressure must be smaller when upward pressure on the top side of the pressure should be smaller when compared to the bottom side. So if the bottom side pressure is more acting in upward direction, and if the top side pressure is less acting in the downward direction, so the resultant pressure will become upwards. So here we can say the upward pressure is more, or we can say upward force is more, which is acting at the bottom of the aeroplane wing to lift up the, or to take, which helps to take out the aeroplane. So if we apply Bernoulli's equation for this top and bottom of the aeroplane wings, top and the bottom of the aeroplane wings. So here at the top, if we consider the parameters with suffix t, and at the bottom, if we consider the parameters with suffix b, so we can use the Bernoulli's principle. So for the bottom case, and if we can ignore the height differences here. So if you consider the height of the aeroplane wing, so it is smaller. So we can take the height is similar for both the top side and the bottom side of the wing, almost same. So we can neglect the differences in potential energy. So if potential energy term is eliminated, so ultimately the Bernoulli's principle will become. So for the bottom side, it becomes Pb plus half rho Vb square, and the top side it becomes Pt plus half rho Vt square. And we are saying that bottom pressure is more and the top pressure is less. So we have delta P equal to Pb minus Pt equal to, so it becomes half rho Vt square minus Vb square. And with the net velocity, net force, F net equal to A into delta P. So I have already considered pressure equal to force by area. So here force equal to pressure into area. So instead of pressure, we are taking the difference in pressure. So when we take the lift force, lift force is nothing but area into change in pressure, delta P naught. And here A is the area of the aerofoil wing. So if we consider the average velocity of the air. So average velocity of the air at the top and the bottom of the airplane wing we consider. So it is given by Vt plus Vb by 2. So Vt means the velocity of the streamlines at the top of the aeroplane wing, and Vb is the velocity of the streamlines at the bottom of the aeroplane wing. So I can consider V average equal to Vt plus Vb by 2, and the difference in velocity is given by delta V equal to Vt minus Vb. And if you write delta P, so from this one you can write delta P equal to, so this one you can consider first. So delta P equal to half into rho into Vt square minus Vb square. So here Vt square minus Vb square, if you consider as A square minus B square, so A square minus B square, you can write it as A plus B into A minus B. So here A plus B by 2, that is Vt plus Vb by 2 will become the, we can write it as the V average. So V average, and into Vt minus Vb, that is A minus B, we can write it as the delta Vm. So ultimately we get delta P equal to rho into, so rho here, and Vt plus Vb by 2, we can write it as the V average, and Vt into Vt minus Vb, we can write it as the delta Vn. So ultimately we get delta P equal to rho V average into delta V. Similarly, if we write delta V, so delta V equal to, if this term comes to this side, it comes delta V equal to delta P by P, delta V equal to delta P by rho average. Delta V equal to delta P by rho average, and if you divide both sides by V average, so make both sides V average divide chesante, we will get delta V by V average equal to delta P by rho V average square into. So if you see here, so we have the lift force is given by F lift equal to A into delta P. So if you replace this delta P by this one, if you replace this delta P by this one, rho average into delta V. So we can write F lift equal to, so A into delta P. So A means, so we can write it as A itself, and instead of delta P, we write it as rho average into delta P. So like this, provided we know the average velocity of the air or the streamlines, and the difference in streamlines are individual velocities of the streamlines at the bottom and at the top of the aeroplane wing, and the provided we know the density of the air and the area of cross section of the aeroplane wing, we can calculate the what is the lift force. So lift force is given by F lift equal to A into rho into V average into delta V. So this is what is about the aerodynamic lift in case of aeroplane. So while coming from South Korea, I have taken some videos on the airport also in Bangkok. So you can see, I will show you later. Meanwhile, you can see here some other videos. So this is the Aerofoil.
It's often said that lift on a wing is generated because the flow moving over the top surface has a longer distance to travel and therefore needs to go faster. The common explanation is actually wrong. This video shows that the air on the top does move faster, but it doesn't reach the end of the wing at the same time as the air along the
Airfoil technology helped human beings to fly. Wind turbines, gas turbines, and hydraulic machines all work on the principles of airfoil. This video will unveil the physics behind the simple shape that revolutionized the engineering world. An airfoil produces a lift force when fluid flows over it. But what is the source of this lift? Is Bernoulli's principle or Newton's third law responsible for it? Or both the effects? Some textbooks point to Bernoulli's principle, but many people reject this claim. Skeptics include NASA scientists and Professor Holger Babinski of the University of Cambridge, who, in his popular YouTube video, proved both experimentally and theoretically that the equal time argument is incorrect. Anyway, we will approach this problem rationally and use computational fluid dynamics and experimentation to support our findings. We will also include an interesting brain teaser at the end of the video. First, let's see what is the argument that uses Bernoulli's principle. The particles on the upper surface should travel a greater distance than the particles on the lower surface. Since both particles should reach the trailing edge at the same time, the upper surface particles should have more velocity than the lower surface particles. This means that according to Bernoulli's principle, there is more pressure at the bottom and less pressure at the top surface. The difference in the pressure generates lift. This argument more specifically is known as the equal time argument. The equal time argument is a beautiful way to explain lift, but it's completely wrong. The first mistake pertains to how two particles starting from the same location reach the trailing edge at the same time. This is a completely absurd argument. There is no law in physics to support it. The two particles can leave for a completely different journey and may not meet in their lifetime. The second mistake is that you cannot apply Bernoulli's equation between two streamlines. Bernoulli's equation should be applied strictly along a streamline. Even after pointing out these mistakes, if you still support this widespread myth, just take a look at this shape. According to the equal time argument, this surface should also produce a lift force. And this surface, the same argument indicates that this should produce an incredible amount of lift. Bernoulli's equation is completely right. It is just Newton's second law of motion applied along a fluid streamline. Some people applied it incorrectly and caused confusion. Now, we will investigate the science behind lift generation by applying the laws of physics correctly. The particle approaches the airfoil and takes a curve as shown, but after the curve, why doesn't it move straight as shown? Examine this curved motion more closely. In order to take the curve, there should be more pressure at the top of the particle than at the bottom. This will supply the centrifugal force. The higher pressure pushes the particle downwards, which is why the flow is always attached to the... This effect is known as the Coanda effect. Spheric. We know in a curved flow, the pressure should be larger. So at the top, the pressure will decrease as we move towards the airfoil. Bottom reason, pressure should airfoil. The difference in pressure is what causes the lift. Basically, the introduction of the airfoil makes the flow curved. This curvature generates the pressure difference and the lift. This means that more curvature translates to more lift. But then, why are airplane airfoils not shaped like this? The reason is to give structural support and a space for accommodating the fuel tanks. Is there any fundamental law of physics that justify the lift rather than this fluid mechanics-based explanation? Yes, Newton's third law of motion. You can see that the airfoil deflects the flow as shown, or it pushes the flow downward. So, according to Newton's third law, the air also should push the airfoil in opposite direction with equal magnitude. This results in lift. In conclusion, the deflection or curvature of the flow caused by the Coanda effect generates the lift. If you find that others still support the equal time argument, ask them to generate lift from this surface. If they are too lazy to do so, we will do it for them. For this simple high-quality CFD analysis to prove the same thing. And what we have discussed so far, here's one brain teaser for you. In actual experiments, you can see that the air at the top of the airfoil moves much faster than the air at the bottom, and they never meet.
So this aerodynamic lift can be explained by in terms of two theories. One is through the Bernoulli's principle, and one is Newton's third law of motion. But here we are concentrating on the Bernoulli's principle, how it is applicable for the aerodynamic lift. So we limit our discussion to only this part. So when we say here the air is moving downwards. So as a result, according to Newton's third law of motion, so Newton's third law of motion, for every action there will be equal and opposite reaction. So when the air is moving fastly on the top of the aeroplane downwards, so in the same velocity, the aeroplane will be moving this side towards the upward direction from left to right. So like this, it will be taking off in the opposite direction of the streamline flow. But here we are limiting our concentration only to the how the Bernoulli's equation is applicable for the aerodynamic lift. So we are not discussing here about the Newton's third law of motion because it is not the incident. We are focusing on our attention only on how the Bernoulli's equation is applicable for the aerodynamic lift. So here, because of the velocity variations on the upper surface of the wing and the bottom surface of the wing, pressure differences occurs, and due to this differences, the aerodynamic lift is occurring, and as a result, the aeroplane is being lifted upwards and it is taking off. So that lift force we can write using the formula F lift equal to A into rho into V average into delta V. So this is about the aerodynamic lift. And if you see here, one more important point. So when the takeoff takes place, means there is a upward force. So as aeroplane moves fast on the runway. So before taking fly off, the aeroplanes move fast on the runway. So as the aeroplane moves faster on the runway, so the velocity of the streamlines difference occurs here. While the aeroplane is moving faster on the runway, the velocity is on the upper surface of the layer will upper surface of the aeroplane will become larger and the bottom surface will become smaller, and they will make the pressure difference. It means at the bottom of the wing, the pressure will be more, and at the top of the wing, the pressure will be less. As a result, the upward pressure, upward force, or what we can call it as the aerodynamic lift will take place, and when the upward thrust force, what we call it as upward thrust force, or aerodynamic lift force, balances the weight of the aeroplane. When the upward thrust force or the aerodynamic lift force balances the weight of the. So here, if you see, the weight will be acting downwards. Weight of the aeroplane will be acting downwards, so whereas the upward thrust or lift force will be acting upwards. So when this downward force, that is weight of the aeroplane, is balanced by the upward thrust force, because of this variations in pressure occurring because of the variations on velocities of the streamlines, the takeoff of the aeroplane takes place. So that one you can see here also with the help of videos what I have recorded while I am coming from South Korea to India on August 1st, 2010. So here as you are able to see, so these are the some pictures of the aeroplane I have taken in Bangkok airport, I think. So here this is the path which is used by the passengers to enter into the aeroplane or to exit from the aeroplane from the airport. And here if you see the video, so here the aeroplane is coming to the airport. So here it is coming to the airport. So here it is coming. You can see. So the aeroplane is entering into the airport. We are going to see the aerofoil wings traveling on horizontal line. There are more aeroplanes entering into the airport. I will show you one more video. What happens when it is taking off. So here the aeroplane is moving on the runway very fastly before taking off. So here now it's just take off. They can take off. So when the takeoff happens, when the upward thrust is balanced by the weight of the aeroplane, the takeoff takes place now. When upward thrust or the upward dynamic lift is balanced by the weight of the aeroplane, then takeoff takes place. I will show you in some larger video also. So here you are able to see. Here one aeroplane is moving on the runway very fastly, so that the pressure differences occurs at the top and bottom layers of the aeroplane. And now when so it is taking off now from its runway. So when the weight of the aeroplane is balanced by the upward thrust or lifting force or aerodynamic lift, it takes takeoff. So it is going up and up in the sky. You are able to see here. So here it is. Okay, it is now again repeating. So this is what about the how the aeroplanes take off. Is it clear to you now? So aerodynamic lift is nothing but due to pressure differences. So velocity of the streamline difference happens due to the structure of the aeroplane wing or aerofoil, and due to this velocities in the streamlines, pressure differences occurs in such a way upward thrust is more to favor the takeoff of the aeroplane. Similar things you can see here also, I think.
Considered to be a pioneer of aviation, he became known as the glider king. He carefully examined the flight of birds and was the first person to make well-documented, repeated, and successful gliding flights. At the beginning of the 20th century, engine-powered airplanes could fly long-distance flights, such as the first transatlantic crossing. But even today, we really don't know for sure why airplanes can't fly. However, wind tunnels with powerful fan systems and equalizers have been used to shed some light on it. In a wind tunnel, we can see, for example, that air passes faster on the top than it does on the bottom of an airfoil. But why? First, let's take a look at an important principle that Bernoulli discovered in the 18th century. Bernoulli found out that fast-moving liquids or air exert less pressure than slow-moving liquids or air. As a result, the pressure on top of the wing is much lower than the pressure below it, because the air moves faster on top of the wing. This produces a force that pushes the wing and consequently the airplane upwards. But why is the airflow on top faster than the air below the wing? By carefully examining the airflow around an airfoil, we see that vortices are being generated. These vortices are called wake turbulences and become visible thanks to the fog. The theory says that a vortex in the form of a circulating airflow will build up around the wing. This circulation increases the velocity of the airflow on top of the airplane. So the first theory said that during the starting phase, a vortex builds up that causes the creation. However, in another theory, Newton's laws are used to explain why airplanes can't fly. This theory says that the wing diverts air down. Here, a key concept is the Quanta effect. The Quanta effect applies as soon as a moving jet of fluid meets a solid surface and follows this surface around the curve. This is also true for an airfoil. The form of the airfoil, however, is not as important as the angle of attack. That is, the angle between the airfoil and the oncoming flow. The higher the angle of attack, the higher the lift. However, the aircraft will be in a stall if the angle of attack is too high, then no lift is generated. Even if there are other theories, this animation has given you an overview of the most widely accepted ones.
Over the last few decades, airplanes have certainly revolutionized the way we travel. But have you ever thought of how it flies? How does it navigate? We will get answers for these questions from this video in a simple yet scientific way. We will also explore how the flight is controlled in a real-time manner. First, let's look at some history. Many crazy flying machine designs were tested in the 19th century because of mankind's quest to fly. Finally, one attempt succeeded. Yes, you are right. It was the flight of the Wright brothers. Their aircraft was a success thanks to an interesting phenomenon of physics, the airfoil technology. The wing of their aircraft was able to produce a lift force in an ingenious way. The wings had a curved shape. This shape pushes the gushing air downwards as shown. Newton's third law of motion comes into picture here. If the wing pushes the air downwards, the air should also push the wing in the opposite direction with an equal magnitude. This eventually results in the lift force, and the aircraft will be able to fly off the ground. Even today, the airplanes make use of the same airfoil technology to fly, but with a highly aerodynamically optimized airfoil shape. Thrust force makes an airplane move forward. To produce this thrust, a turbofan engine is used in modern civil aviation aircraft. Reaction force of high-velocity exit jet gives the turbofan engine the thrust force. To produce this high-velocity jet, the incoming air is passed through a compressor, combustion chamber, and turbine stages. The engine also derives the thrust force from the fan's reaction. Thus, the turbofan engines produce a great amount of thrust and make the airplane move forward. As discussed earlier, when the airplane moves forward, the relatively flowing air over the wing will produce a lift force on the wings. Just pause for a moment here and have a close look at the wing. You can note that the wing of a modern aircraft is a collection of different parts. During the takeoff, the flaps and slants are extended downwards as shown. This increases the wing area and curvature of the airfoil. As the curvature increases, air will be deflected more. Thus, a greater lift force can be derived even at low airplane speed. As the airplane speed increases, the lift force rises.
So when the weight of the
Finally, when the lift is more than the gravitational force, the plane takes off. During the normal flight, flaps and slants are put into its original position. It is interesting to note that different forces acting on the airplane balance exactly each other during the normal flight. Now let's get into the core of the flight navigation. You can navigate the airplane the way you want with the help of 3 different wing attachments: aileron, elevator, and rudder. Pilots use them alone or together depending on the situation. Assume you want to descend the airplane. You can just lower the elevator. This will deflect the flow as shown and will produce a lift. The lift force will create a moment that will make the nose of the plane go down. If you want to climb up, just do the reverse. Now let's assume the airplane has to change its path. You must have an obvious answer in your mind. Just turn the rudder. Of course, turning the rudder will produce a lift force and make the airplane turn as shown. But such a sudden change in flight direction may cause passenger discomfort. The professional way is the use of ailerons. Just make one aileron go up and the other down. This will cause difference in the lift forces and the airplane will roll. Now observe what happens if the airplane still goes up. it's clear that the airplane has changed its path. Unlike the previous method, the airplane orientation has not changed here. All these movements of flaps and other devices are controlled from the cockpit using a fly-by-wire system. In FBW systems, the controller computer governs exact movement of actuators for smooth operation. You can see the different controllers pilots use to navigate the airplane. Fuel required for the airplane is stored in the large tanks of the wing. During landing, it is required to increase the drag. For this purpose, flaps and slats are activated again because they have drag raising capability too. A wing attachment, called a spoiler, is also activated to increase the drag further and reduce the lift. An interesting mechanism is used for lowering the flaps. The mechanism will rotate as well as displace the flaps. We hope you enjoyed the flight journey by exploring the science behind the airplane operation. Thank you.
This is the aerofoil, the aeroplane wings are used to take the takeoff or land like this. I hope you have understood what is meant by aerodynamic lift and how the aerodynamic, the Bernoulli's theorem is applicable in case of aerodynamic lift. Hope you enjoy. Thank you. And now we will leave here. And in tomorrow's class, on Monday, we will start the next topic, that is viscosity. Thank you. Have a nice day. Bye.
This conference will now be recorded.